So we've mentioned scuba diving before in this chapter. We're going to revisit that a little bit. So when a diver breathes compressed air, the pressure of that air being compressed, right, is higher than atmospheric pressure. Well, if the total pressure is higher, then the partial pressure of oxygen is also higher. And that's not necessarily a good thing. So this is the safe range of oxygen pressure. So air at the surface is about 0.21 atmospheres of oxygen. That's the partial pressure of oxygen, because air is about 21% oxygen. And so you can have more oxygen and be okay. This would be 100% oxygen at atmospheric pressure, which, you know, athletes sometimes do that on the sidelines. You could handle up to 1.4 atmospheres at exertion, but if you get up to past 1.6 atmospheres of oxygen, you get into what's called oxygen toxicity. And this is something I would really like everybody to take away from my chemistry class, that everything is toxic at some point, right? And if everything's toxic, it's at some level. Are we going to go around being afraid of everything? No. You have to be aware of what's going on. But we don't have to be afraid of everything. So too much water is toxic, too much oxygen is toxic. But not enough will kill you also.
What about those people who have like pure oxygen tanks pumped into their home? And they just have that like
so pure oxygen at 1 atmosphere of pressure is not going to be a problem. It's when it's pressurized that then you get too much oxygen in your blood. And then, of course, people with breathing difficulties aren't able to get enough oxygen from the air, and so they may need to be breathing pure oxygen. But again, that's going to be at normal pressure. Anything where you just have like one of those nasal cannulas with stuff going into your nose for you to breathe, that's going to be at atmospheric pressure. That's not going to cause a problem. Hypoxia, that prefix hypo means low. So hypoxia is our oxygen starvation, and that happens when oxygen pressures are too low. And that's much easier to have happen. You go up in the mountains where the air is, we say it's thin, right? There's less oxygen up there because the air pressure is less. And so then you get out of breath. Compressed air is mostly nitrogen, and so if you're breathing compressed air, you're also going to get a higher partial pressure of nitrogen. And that's not good for you either. If you get above 4 atmospheres of nitrogen pressure that you're breathing, that can cause nitrogen narcosis, sometimes called rapture of the deep. Okay, that would happen when you're deep down breathing compressed air, and the symptoms are not unlike alcohol intoxication. And so, you know, rapture of the deep, you're probably feeling pretty good down there, but it's also going to be impairing your judgment. And so that's not a good thing when you're 30, 40 meters under the surface of the water. You've probably heard of the bends. So what happens there is someone's been breathing compressed air, and they come back to the surface too quickly. And so this high concentration of nitrogen in the air you've been breathing causes the nitrogen levels in your blood to be higher as well. If you don't come up slowly and allow your body to remove the nitrogen, it can actually form bubbles in your blood, and that causes a lot of pain and other problems. And so that's why it's important to come up slowly to let your body get those extra gases out. So here's a problem dealing with partial pressures and mole fractions. A diver breathes a heliox mixture. Okay, so what's heliox? So high pressures of oxygen, high pressures of nitrogen aren't good. So if you're going to go far, far below the surface of the water and you need high pressures, what are you going to breathe? Well, you need to breathe something else. So heliox is a mixture of oxygen and helium. So you can control the amount of oxygen. The helium is not going to affect you other than making your voice really high, but you can't really talk underwater anyway, so that doesn't really matter. So this heliox mixture has an oxygen mole fraction of 0.05. So that's less than air. Air is 0.21. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So how do we even think about this problem? We draw scribbly lines. That's what we do. So we've got a mole fraction. So the mole fraction of oxygen is 0.050. And we're looking for total pressure, and we want the partial pressure of the oxygen to be 0.21 atmospheres. We have to breathe pressurized gases underwater because otherwise we can't even expand our lungs. So it has to be at a high pressure, but we would like the partial pressure to be the same as it is on the surface because that's a good place for our bodies to be. And so they're asking us, what's the total pressure? Well, there's an equation that relates these. The partial pressure of a gas is equal to its mole fraction times the total pressure. So we can solve this for total pressure, and we find that the total pressure is equal to the partial pressure over the mole fraction. So in this problem, the total pressure is going to equal the mole fraction of oxygen divided by the partial pressure of oxygen, 0.050. That doesn't have any units, divided by partial pressure . You see what I did? Yeah, I did. So I did this one right, and then when I went over here, I switched it around, and that's why I kind of paused there because the units aren't working out. Okay. Let's fix that. So it's partial pressure on top and mole fraction on the bottom. So partial pressure is 0.21 atmospheres. Divide by the mole fraction. That looks better. So that's going to be 4.2 atmospheres. So this is why divers often will have two tanks. And as they go down, they're going to switch from compressed air to heliox. And then as you come back up, you need to switch back. So it's, it's a little more complicated than just going swimming. Any questions? Gases are kind of cool to work with, but they're a little bit difficult too because you can't just stick them in a beaker, right? You have to contain them somehow. So if you're working with an experiment or a reaction that generates gases, how do you collect the gas? Well, a common method is by displacement of water. So you collect the gas by having the gas displace water from a container. There's a picture. So here's our reaction. It's generating hydrogen gas. We can collect it in this inverted beaker. So this started out full of water, no gas in there at all. And we've got this tubing that goes from the reaction test tube under here. The gas is trying to escape, and so it's going to bubble up through the water and will displace the water. It's called collecting a gas over water. Because there's water there and water evaporates, there's also going to be water vapor in that area, in that gas, right? It's going to be a wet gas. So if we want to know what the pressure of our gas that we just made is, we need to subtract the partial pressure of the water vapor there. The partial pressure of water is called the vapor pressure. It depends only on the temperature. So that's kind of convenient. You can just measure the temperature of your collection apparatus, and then you can just look up the vapor pressure of water. You don't have to do anything fancy. So this is a sort of table, and you do not memorize things like this. You just look them up. So like at 25 degrees Celsius, the vapor pressure of water is 23.78 millimeters of mercury. So when we collect this hydrogen gas, here we have all the hydrogen that we were collecting plus the water vapor. So if the pressure here, whatever this total pressure is, you subtract off the pressure of the water vapor. This is why I don't usually lecture this long, because whatever. Okay, example. Sample of acetylene collected over water. Total gas pressure 738 torr. Volumes 523 milliliters. At the temperature of the gas, 23 degrees Celsius. The vapor pressure of water is 21 torr. How many grams of acetylene are collected? Okay, lots of words. Bunch of numbers. Let's pull out the numbers. So we've got 738 torr. And that says the total pressure. So let's label that P total. And we've got a volume. Volume is 523 milliliters. And the temperature of the gas is 23 degrees Celsius. And then they're telling us that the vapor pressure of water is 21 torr. I'm going to stick that up here. And we are asked to find the mass in grams of acetylene. So this is one we might want to make a path for. So we want grams of acetylene, C2H2. And how are we going to get there? Well, what do we often convert grams to? Moles. So if we had moles of acetylene, we could use the molar mass and get to grams. How do we get to moles of acetylene? PV equals nRT. So we're going to use PIV-NERT. PV equals nRT, and N is going to equal PV over RT, just rearranging the equation. So this P, is that the total pressure of the gas? No, because that would give us the total number of moles. We just want the moles of acetylene. The other thing that's in there is the water. We don't want the water. So we're going to subtract. So 738 minus 21 is 727 torr, right? That equals the partial pressure of the acetylene. Yeah, it is 717. See, that's good. You're paying attention. I won't even pretend that I did that on purpose. So torr's not great here, so we got to convert to atmospheres. 0.943. So we've got our pressure, 0.94342 atmospheres. And then we need the volume in what unit? Liters. So liter on top, milliliters on the bottom. Milli means 10 to the minus 3, so that goes on the other side. 0.523 liters. Divided by R. And then the temperature, 23 degrees Celsius. That's got to be in Kelvin. So I'm coming up with 0.0203 moles. Anybody else get that? Cool. So then we have to convert that to grams. So we need the molar mass. We're given the formula. So it's 2 times 12.01. Plus 2 times 1.008. $26.036. Coming up with 0.52853 grams, 0.529 grams. Any questions? There's like an infinite variety of problems that can be asked using the ideal gas law. And so we've done this part several times now, haven't we? In different sorts of problems, but we end up using this to find the moles, and then we do something else with it. Here's another one. Common way to make hydrogen gas in the laboratory is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? So this is similar to the last problem. Collecting a gas over water, they're asking for mass of the gas. So we're going to need the pressure, the partial pressure of hydrogen. And that's going to equal the total pressure minus the partial pressure of water. We're given the total pressure, 742 millimeters of mercury. Did they give us the vapor pressure for water? No. We have to go look it up. So in this table, at 25 degrees Celsius, which is the temperature specified, the pressure of water in millimeters of mercury is 23.78. So I've got 742 minus 23.78. 718.22 millimeters of mercury. But you got to convert that to atmospheres, right? So divide by 760. 0.94502 atmospheres. So this is the same pattern as the previous example. We need to calculate moles of hydrogen and then convert that to grams and then to milligrams for this one. So got our pressure, and we've got a volume of 154.4 milliliters. So we have to convert that to liters, 1544 liters. And the temperature's 25 degrees Celsius, so we have to convert that to Kelvin, so that's 298.15 Kelvin. N equals PV over RT. So pressure 0.94502 atmospheres times the volume 0.1544 liters divided by R and the temperature. All the units are going to work out there. So I have pressure times volume divided by R and divided by the temperature. 0.0059638. That's moles of hydrogen. So we need to convert that to grams. What's the formula for hydrogen gas? H2. So this is 2.016 grams per mole. But it wants the answer in milligrams, so let's just add that on here. Multiply by milligrams, divide by grams. Milli means 10 to the minus 3. So we put 10 to the minus 3 where milli is not. And I'm coming up with 12.0 milligrams. Any questions? Good way to practice these is to go on YouTube, get the video, go to the part where it just shows the question, and try to do it yourself. And then if you get stuck, play the video and see what I did, and keep doing that until you can do these. right? It's practice.